We are absolutely surrounded by incredible technology every single day. I mean, it's everywhere. But have you ever really stopped and wondered how it all actually works? Well, today we're going to pull back that curtain and find out what's really going on inside your phone, your laptop, and pretty much every smart device you own.
So get this. The phone that's probably in your pocket right now has more raw computing power than all of NASA had back in 1969 when they landed a man on the moon. That's insane, right? But here's the thing. At its very core, your phone and the world's most powerful supercomputer follow the exact same surprisingly simple principles. So, what's the secret?
Well, the secret is that every computer, and I mean every computer, from a massive server farm to your little smartwatch, really only does 4 fundamental things. Once you get these 4 jobs, you've pretty much got the foundation of all modern computing.
It really is this straightforward. First, a computer needs input. It's got to take in information, from you typing on a keyboard or speaking into a mic. Second, it has to process that info. It needs to think about it, to do something with it. Third, it creates an output, showing you the result on a screen or playing a sound through speakers. And finally, number 4, it needs storage, a way to remember that information for later. Input, process, output, storage. That's it. That's the playbook for everything.
And this brings us to this key idea of a computer system. See, the magic isn't in any single part. It's about all these different pieces, all the physical hardware and the invisible instructions, the software, work together as one single unit to get those 4 jobs done.
Okay, so if a computer is a system, then every system needs a control center, right? It needs a brain. So let's dive inside this digital brain and see where the real thinking actually happens.
That brain is the central processing unit, or, as you've probably heard, the CPU. It's this absolute marvel of engineering that's at the heart of the entire operation. It's the part that takes in data, crunches the numbers, and sends the results back out. It's the boss.
And this brain basically has 2 main departments. You've got the arithmetic logic unit, the ALU. That's the mathematician. It's the part doing all the adding, subtracting, and logical comparisons. Then you have the control unit, or CU. Think of the CU as the project manager or the traffic cop. It doesn't do the math itself, but it directs all the traffic, telling the ALU, the memory, and everything else what to do and when to do it.
Now, a brain is no good without memory. Computers have 2 main types. First, there's RAM, which is kind of like your short-term memory. It's the computer's workspace for whatever it's actively doing right now. But it's volatile, which is a fancy way of saying when the power goes off, poof, it's all gone. On the other hand, you have ROM. That's non-volatile. It's more like the computer's deep-seated instincts, the basic instructions it needs just to wake up, which are burned in there permanently.
So, to put it another way, think of primary memory, like RAM, as your workbench. It's super fast, right there next to you, ready for active tasks, but you only have so much space. Secondary memory, like your hard drive or SSD, well, that's the giant filing cabinet down the hall. It's a little slower to get to, but it's where you can store pretty much everything forever.
So we've seen the parts, but how in the world did they get so tiny and unbelievably powerful? The journey from the very first computers to the devices we carry around today is honestly one of the most incredible stories in all of human innovation.
It all started way back in the 1800s as this purely mechanical dream. By 1945, that dream became ENIAC, a monster of a machine that literally filled an entire room. But the real game changer, the moment everything changed, was in 1971 with the invention of the microprocessor. This was the first time we put an entire computer brain onto a single, tiny little chip of silicon.
But here's the wild part. Even before that, back in 1965, a co-founder of Intel named Gordon Moore made this incredible prediction. He said that the number of tiny electronic switches, called transistors, that we could cram onto a chip would double about every 2 years. And at the same time, the cost would get cut in half. It was basically a roadmap for exponential growth.
So was he right? Oh yeah. A modern processor, the brain in your laptop or phone, has over 10 billion transistors. No, that is not a typo. 10 billion. Let that sink in for a second. That explosive growth, Moore's Law, is the engine that powered the entire digital revolution. It's why your phone is more powerful than a room-sized machine from the 60s.
All right, so let's zoom back out. We have this super powerful brain. We have memory. If we put all these physical components together, what do we actually have? Well, the absolute best way to think about all this hardware is as a body.
It's really a perfect analogy when you think about it. The CPU? That's the brain. The RAM and ROM act as its memory. All the input devices, your keyboard, your mouse, your microphone, those are its senses. And the output devices, like the screen and speakers, that's its voice and hands. And what connects it all? The system bus. All the little wires that act like a nervous system, zipping signals between every single part.
So, okay, we've built a complete digital body. It has a brain, it has memory, senses, even a nervous system. But right now, it's just a really sophisticated sculpture. It's an empty vessel. Without any thoughts, without any instructions, it has no purpose. It can't actually do anything on its own.
So what's the missing piece? What's the spark that brings this digital body to life? The answer is software. If the hardware is the body, then software is the mind.
Software is basically the ghost in the machine. It's the complete set of instructions that you can't physically touch, but it's what tells all that physical hardware what to do. It's the consciousness, the mind, that animates the body. And they absolutely need each other. Without software, hardware is just an expensive paperweight. And without hardware, software has nowhere to run.
And there are two main kinds of thoughts that this mind has. First is system software, like your operating system, Windows or iOS. Think of this as the subconscious. It manages all the background stuff, managing the hardware work, managing files, all the things you don't actively think about. Then there's application software. This is the conscious thought. It's the specific thing you choose to do, like opening a web browser, writing an email, or playing a game.
So, we have a body and we have a mind. The final piece of the puzzle is, how do we talk to it? How do we communicate? Because our conversation with computers has changed dramatically over the years. In the early days, we had to speak their language. We had to type these precise, unforgiving text commands into a command line. Then came the huge breakthrough of the graphical user interface, the GUI. Suddenly, we had a shared visual language of icons and folders that we could just click on. Today, the conversation is even more natural. We just physically interact by touching and swiping. And now, we're just talking to them, using our voices and gestures. With every step, we're teaching them to understand us, not the other way around.
So there you have it. We started with just 4 simple jobs. And from those, we built a CPU brain, we gave it memory, we wrapped it all up in a hardware body, and then we brought it to life with a software mind. These fundamental building blocks are working together right now inside the very device you're using for this explain.
And that leaves us with one final, kind of mind-bending thought from the father of computer science himself, Alan Turing. He said that a computer would deserve to be called intelligent if it could fool a human into believing it was human. As we keep making our computers more and more like us, giving them bodies, minds, and natural ways to communicate, that line he drew is getting closer and closer. The question is no longer just how they work, but what they are becoming. Thanks for watching.